Today we start a series on advanced covalent bonding. We've already learned the basic idea behind covalent bonding. We've learned how to draw Lewis structures. We've learned how to recognize a polar covalent bond, and even to recognize whether an entire molecule is polar or not. But now we're going to take a more in-depth look at explaining why the VSEPR theory works, in fact, when it seems contradictory to what we know about atomic orbitals. And then we'll look at a more sophisticated theory that actually is the best model we have for covalent bonding, but it's kind of hard to understand, so we'll just scratch the surface of it, called molecular orbital theory. The theory we're going to look at now is called valence bond theory. And the basic idea is that bonds form when atomic orbitals overlap with each other, and then they share the two electrons, each from a different atom, that have a paired spin, so one spin up and one spin down. The result is that the electron pair that's shared has its probability density, or its likelihood of being found, concentrated in the region of overlap, in the region between the two nuclei that are being bonded to each other. And the potential energy of that bond is lowest, in other words, the energy stored in the positions of those nuclei is lowest when these atomic orbitals are overlapped the most that they possibly can be. So in other words, when the nuclei are as close as they can possibly be to each other. So here's an example of valence bond theory at work in hydrogen. Each hydrogen atom has a 1s sublevel that's shown by this box here with one electron in it. So each of these is 1s. Two separate hydrogens, and we notice that the spins happen to be opposite here. When the hydrogen molecule, an H2, forms, what happens is this orbital and this orbital overlap with each other and form this new kind of region where the probability of finding that electron pair is highest in between the two nuclei, and it's lower on the outsides. Another example would be with F2. Let's see where the bonding actually happens by drawing orbital notation for fluorine. I'm only going to look at the valence shell, so that's the second shell. So 2s and 2p is where fluorine lives in its valence shell. And for fluorine, there are 7 electrons in that valence shell, and that's how they're arranged. So one fluorine maybe has this orbital notation, and the second fluorine looks very similar to that, only a spin down. So here's where the sharing occurs. The overlap is going to be one of each of the 3 p orbitals overlapping with each other. So in this picture, we see the fluorine nucleus here and the second fluorine nucleus here. So this is like fluorine 2, fluorine 1, and they're going to merge. The overlap is going to occur between these orbitals, and this is the final bonded situation. You can see the likelihood of finding that electron pair, that shared pair, is highest in here between the two nuclei, and it decreases on the other side. Whereas before, in the atomic orbitals, the lobes were equal sizes on both sides of the nucleus. Now the outside lobe is smaller, the inside lobe is bigger, and so that's why the bond occurred. Now let's take a look at H2O. How could this happen? I'm going to look at an oxygen first and start by drawing oxygen's electron configuration notation. So oxygen is, looking only at the valence level, 2s, that's full, and 2p, and it's 1, 2, 3, 4. Hydrogen. Well, one of my hydrogens has a 1s sublevel, and I'm going to put a spin down electron there. My second also has a 1s, and I'm going to put a spin down electron there. So where's the overlap? Well, this 2p is going to overlap with the 1s of one of the hydrogens, and this other half full 2p will overlap with the other 1s orbital of the second hydrogen. And so that's how the H2O forms. Now this doesn't explain some things that we know about water. We know that water is a bent 105 molecule. So we've got the two H's here, 105 degrees apart from one another. But we also know that p orbitals, I'm going to kind of draw them here, this O in the center, are 90 degrees from each other. So if this is really what's happening here, you would think that one of the H's would be attached at a 90-degree angle from the other H. So there's a discrepancy between what we know to be true about atomic orbitals, that p orbitals are 90 degrees from each other, and VSEPR theory, which matches reality. VSEPR theory predicts there's going to be a 105-degree bond angle. In fact, there really is a 105-degree bond angle in water. So something about this theory doesn't work, doesn't match reality. Well, the explanation for this is that when bonds occur, you don't have atomic orbitals anymore as they originally existed in many cases. In fact, in most cases. When bonds form, atomic orbitals change. They do what's called hybridization to form hybrid orbitals. So you no longer have separate S's and P's, you have sp hybrid orbitals, and they arrange themselves according to VSEPR theory in the arrangements that we've seen for electron geometries. Sometimes it's not even possible to understand how a bond could have occurred looking only at atomic orbitals. An example of this would be the beryllium in BeH2. Here's beryllium unbonded normally. Valence shell, 2s, 2 electrons, 2p, no electrons. Now no sharing can occur here because this beryllium 2s orbital is already full. There's no room for any overlap. In fact, this is what happens. When bonding occurs, the theory is that hybridization happens, and instead of S's and P's being separate, that S orbital and this P orbital kind of combine, and they hybridize and make an sp sublevel. And then, by Hund's rule, I'm going to get the 2 electrons in separate orbitals. That still leaves me with 2 unhybridized p orbitals, but they don't have anything in them. So now we can have a BeH2 because the 1s orbital from one of the hydrogens and the 1s orbital from the second hydrogen can overlap there, and we have a linear molecule. So sp hybrid orbitals are not s's or p's. They're something new. For sp hybridization, these are the atomic orbitals that are available. There's 1 s orbital, which is spherical, and 3 p orbitals, which are those dumbbell-shaped 90 degrees from each other orbitals. When they hybridize, here's what happens. In sp hybridization, an s and a p orbital combine and create 2 new orbitals that are in the same sublevel. They're called sp hybrid orbitals. Here's what they look like. Low concentration on one side of the nucleus and a higher concentration on the other side of the nucleus. The orbital set, when it goes together, shows a 180-degree bond angle because these hybrid orbitals are going to be as far apart as possible. Now notice that by having the interior lobe of the hybrid orbital be small and the exterior lobe much larger, overlap between the beryllium, which would be in the center here, and the hydrogens, which would bond on the outside here, will be much higher. And so energy could be minimized, and so the bond becomes more stable. So sp hybridization explains how the bonds can even happen, why maximum overlap can occur to make the bonds more stable, and why we get the geometries that we get. Here's an example of an sp hybridized carbon. Let's take a look at what this would look like with orbital notation. So carbon in the highest shell is 2s full, and then 2p has 2 electrons in it because there are 4 electrons total. And by Hund's rule, they're going to split up into separate orbitals. And an sp hybridized carbon is going to look like this. sp sublevel is made from 1s and 1p orbital. That leaves us with 2 unhybridized 2p orbitals. So here's how the electrons can then arrange themselves. I could have electrons 1 each in sps and 2p's. That's sometimes what happens. I may end up with a pair in an sp and a lone electron in an sp, and one of the 2p's be empty. There are different ways that it can play out depending on the bonding situation. This is what it would look like physically. You'd have the 2 sp hybrid orbitals reaching out toward another atom to make a bond, and then the unhybridized p's still look like p's. They're 90 degrees from each other, and they have the 2 separate lobes of equal size. I'm going to show you this little energy level diagram just to show you why this is advantageous. In a free carbon atom that's unbonded to anything, here are the sublevels. We're familiar with these. These are just atomic orbitals. 2s is lower, 2p is higher, and you have 3 orbitals in 2p and 1 in 2s. After hybridization, we now have 2 sublevels. The sp is a little higher than an s was, but it's a little lower than a p was. And now we have still the two unhybridized 2p's. So we have two orbitals here and two orbitals here. These are lower energy. The sp orbitals are lower energy than a p was. And so this allows those electrons from the p to be in a lower energy situation, and that's energetically favorable. Let's look at another bonding situation. Boron in BCl3. Here's a normal boron. Valence shell, 2s full, and 2p has one electron in it. I'm going to draw it like that. In BCl3, boron has to be able to overlap in three different places. And so this is the kind of hybridization that takes place. Three hybrid orbitals are formed from the s and two of the p orbitals. In these, this is called sp2 because it's made from one s and two p's. And then that leaves us with one unhybridized 2p orbital. The three electrons that are in boron are now going to occupy the three orbitals that are sp2 hybrid orbitals so that they can maximize overlap and actually make these bonds with the chlorine atoms on the outside. The 2p here is empty. So where does the overlap occur? Well, I'm going to just take a look at one of the chlorines. Chlorine is 3s, 2, and 3p, 5. Overlap, drawn my spin wrong, but overlap can occur between an unhybridized p and an sp2. Or maybe chlorine itself hybridizes to maximize overlap. What we just saw there with boron is an example of what's called sp2 hybridization. Remember, the orbitals that we have to work with are an s and p's. The one s and the two p's hybridize to make three sp2 hybrid orbitals. Those three regions of electron density, the best they can do is get 120 degrees from each other in a flat surface, and so that's where the trigonoplanar molecule comes from. And again, thinking of the central boron at the 0 point of these three axes, on the one side we have reduced electron density and increased electron density on the other side, where it's going to reach out and maximize overlap with another atom, chlorines in that case. This is an example of an sp2 hybridized oxygen. So what would that look like in orbital notation? Well, oxygen is 2s full and 2p part full. Like that. sp2 hybridization takes two of the p's and the 1s orbital and makes sp2 hybrid orbitals and leaves one unhybridized 2p. So now oxygen could make three bonds by putting three electrons there. Probably it would leave an electron in 2p, and we might have lone pairs in hybrid orbitals. Lone pairs always occur in hybrid orbitals. This is what it looked like physically. There's the oxygen atom in the center. We have three sp2s at 120 degrees from each other, and then we have that one unhybridized p orbital that's 90 degrees from that plane. Another example would be C2H4. Carbon is making three bonds here, one to another carbon and two to hydrogens, and the hybridization that has to take place is sp2 hybridization to make three bonds. So carbon starts out 2s, and then two electrons in 2p orbitals. After hybridization, we have sp2 orbitals, three of them at a lower energy level, and then one unhybridized 2p. And the electrons arrange themselves this way. And since there are four of them, that means apparently there must be another electron in this 2p, which is half occupied. Now, if you draw the Lewis structure for C2H4, you realize that it's double bonded. We are only showing one bond between the two carbons. That unhybridized p, you might be getting the clue, has something to do with multiple bonds. We'll see more of that later. sp3 hybridization is what we get when we have a tetrahedral geometry. In other words, when the central atom is making four bonds to the outside. So it starts with 1s and 3p orbitals. They hybridize and they make four identical sp3 hybrid orbitals. And because they want to get as far away from each other as they can, in VSEPR theory that dictates that tetrahedral geometry. So if this were happening to carbon, which it often does, the carbon atom would be in the center of the three axes here, and on one side you have high electron probability, on the other side you have much lower electron probability than you would have with an ordinary p or equally balanced s. And that allows greater overlap, which means more stable molecules. It also allows the possibility of tetrahedral geometry. If you look at carbon, for example, which often sp3 hybridizes, it would not be possible for it to make 4 bonds with atomic electron configuration. Hybridization is necessary for the bonding to occur. So here's carbon in CH4. This is shown with the hybrid orbitals, the sp3 orbitals in place. What does it look like with orbital notation? Ordinary carbon has 2p with 2 electrons in it and a 2s that has 2 electrons in it in a single orbital. After hybridization, I have sp3 hybrid orbitals, which requires 1s and 3 p's. So sp3 hybridization leaves no unhybridized orbitals behind. Each one of these electrons that was previously in an s or a p is now in a separate sp3 hybrid orbital. This allows overlap to 4 other atoms, and so carbon can bond to 4 hydrogens. Here's another example, ammonia. Nitrogen here is sp3 hybridized. The lone pair goes in a hybrid orbital, and then the other 3 hybrid orbitals overlap with hydrogen atoms to create bonds. So nitrogen normally is in the valence shell, 2s full, and then we have a 2p that has 1 electron in each orbital. After hybridizing to an sp3 orbital set, which is 4 orbitals, we now have a lone pair in 1 hybrid orbital, and then 3 remaining electrons can overlap with 1s's from hydrogens to make the bonds. Let's look at hybridization for expanded octets, and we'll use phosphorus in PCl5 as a kind of an example. Here's phosphorus unhybridized. In the 3s, we have 2 electrons, and this is in column 5, so we have 3 electrons, 1 each, in 3p orbitals. And then we've got d orbitals available, which is a necessity for expanded octets, but there's nothing in them. The hybridization that occurs here is what we call sp3d hybridization, because it takes 1s, 3 p's, and a d. So the s, 3 p's, and 1 d all combined, hybridized, make these new kinds of orbitals that allow maximum overlap, and they're called sp3d hybrid orbitals. That leaves us with 4 unhybridized 3d orbitals with nothing in them. The 5 electrons that are in phosphorus normally now spread out and occupy separate orbitals in this sp3d level. Then they can overlap with chlorine atom orbitals to make the 5 bonds. That wouldn't be possible only with an s and p available. You have to hybridize in a 3d. This is what the shape would look like. Of course, it's the trigonal bipyramidal shape that we're familiar with from VSEPR theory. And the chlorine atoms are going to bond at the ends. They're going to overlap with each one of these hybrid orbitals. That's what it would look like, with the chlorines having their sp3 hybrid orbitals overlapping with the sp3ds of the phosphorus. That's where the electrons all are. We've got lone pairs on 3 places in the chlorines. They're in hybrid orbitals. And the phosphorus in the middle is sp3d hybridized. So let's write in the hybridization. This is sp3, this is sp3, this is sp3, this one's sp3. All the chlorines are sp3 hybridized. And then the phosphorus in the middle is sp3d, which gives us our 5 regions of electron density. 1 there, 1 there, 1 there, 1 up, 1 down. We have one other kind of hybridization because we have 1 additional electron geometry. And of course, that's octahedral. When sulfur hybridizes, in SF4 for example, it goes from this ordinary 3s, 3p atomic orbital arrangement. The 3s is full, 3p's are organized like this. That's normal unbonded sulfur. And then there are 3d orbitals available, 5 of them. They don't have any electrons in them. The hybridization that occurs has to allow for 6 places for electrons to overlap. So we have 6 hybrid orbitals. That requires all 3 P's and an S and 2 of the D's. And so this hybridization is sp3d2. That leaves us with 3 unhybridized d orbitals. The 6 electrons that are in sulfur are now each in their own orbital, and that allows overlap with 6 fluorine atoms, which are going to be sp3 hybridized, to create the 6 bonds. There's the orbital arrangement around the sulfur, sp3d2, or d2sp3 as this picture says. And then at the terminus of each of these things would be overlap with a different fluorine atom in these 6 places to make our sf6. Well, we've only looked at single bonds at this point, and I've hinted that the unhybridized orbitals have something to do with multiple bonds. So our topic next time is going to be how do we deal with the unhybridized orbitals and the fact that multiple bonds are sometimes made.